Okay, so welcome back. We are carrying on with the proof of this exponential improvement on the multicolor Ramsey number, in particular the three-color one is what we're focusing on in these lectures. And we did some important work last week. I suppose we started by giving the overview of what the approach would be, and maybe just to remind ourselves very quickly, the approach is based on having a set of vertices X, which are going to be available to build. We're basically going to try and build a large enough book. What we did on the first lecture last week was reduce our task to just proving the so-called book theorem, which meant we just needed to find an algorithm in a multicolored graph in a certain setting to find a large enough book. And then last class, we managed to introduce the algorithm, which we were going to use to do that. And it involves either you do a color set, where a vertex will join one of the colors. Of course, we want to maintain X, so it's just joined to each of these, each of the TIs of the clique in the respective color. And X will join just in that clique, just in the same color. And for each I in 1, 2, 3, we'll also have a set yi, which just joins to the clique ti in the correct color. And so the idea is we want to do this for long enough that this clique gets big enough that we can use this book to find the book we want to complete the book theorem. I mean, it happens to be that we want T to get up to K over 2 to the 30. That's the numbers we've picked for this particular proof, and we need to do that and keep y large. So in a way, maybe I should say, what are the challenges, what are the things we still need to do? This will sort of be a plan for what we need to do this week in the two classes. So, well, one thing that's a bit left over was we didn't actually prove the key lemma. We said it would be a consequence of the geometric lemma, but we didn't prove it. So to do, we want to do, well, geometric implies key. Geometric lemma implies the key lemma. We want to then, the most important thing will be understanding, as you apply the algorithm, what can you say about the evolution of the size of the sets? If one of our sets is shrinking too quickly, then it doesn't matter how many other ideas you think are cool and interesting, or whatever else you think about all the proof will just fail. So it all comes down at the end of the day to making sure these sets stay big enough throughout the process. Now, a lot of the time, giving courses like this, you can just kind of give a sketch. It's probably believable, this stays about this size. For some reason, I'm trying to do this this course, because it is possible. We can just go through the details and see it all really does work. So let me put here, one thing what I want to do is understand the evolution of the size of X. Another thing we want to do is understand the evolution of the size of the Y's. And these we'll do in the next class, and that will complete the proof, obviously. One thing we're going to do today is something about what are the behavior of these minimum degree conditions, and we'll see some properties of boosts. Because in a way, when you're doing the color steps, it's kind of all, it's what you plan to do, it's what you want it to do. And so it all really makes sense, you're going to be able to make your nice book of the right size if you spend all your time doing these nice color steps. The boosts, while they have an advantage, in some sense, they're in another sense wasteful, right? Because you end up having to zoom into subsets without doing a real step. So it's going to be important to understand how many boost steps there are and how much of the sets you use up do. So basically today, our objective will be to do these two. In other words, to show the key lemma does follow from the geometric lemma, and then to see some background on the behavior of the minimum degree conditions throughout the process, and somehow bound the number of boosts and how much they affect the size of the set. So let's get on with our first task then, which is showing the key lemma is a consequence of the geometric lemma. They have a lot in common in these statements, really. Well, a little bit anyway. So here is the situation when you have a coloring, a three-coloring of a union of sets. You're given some alpha 1, alpha 2, alpha 3. Just remember what we have to prove. And we want to be able to find a vertex in X, a subset X prime in X and Y prime in YI. YI prime, you should basically think of it as the neighborhood of X on the other side. Because it's going to have size. This would be the minimum size allowed in the neighborhood. We're just going to ask for the Y prime to be as big as its minimum. And we want it to be a subset of the neighbors in color around X in that set. And then what else do you want? Well, either this is going to correspond to the case in algorithm where you do a color set. You want that the set in X, the X prime contain X is also contained in the neighborhood of the same color. And you want the lower bound on its size. And in that case, you allow yourself to lose a little bit of the minimum degree condition, but you want to know you lose at most alpha. Or in the other case, if this is not possible, you want to know that for some large lambda, you can get a boost in the density of lambda times alpha I without going down too much in terms of the size of Xi. And what we're going to try and get this as a consequence of is the geometric lemma, which we remind ourselves here. You have a finite set, you have two ID random variables taking values in that set, and you have three functions in that set to RD, then you sort of want either there's a good probability that when you map these points into RD in three different ways, you have either a good probability that the inner product is at least -1 in all of them, or in at least one of them, you put some decent weight in the tail. And so you get a probability with this at least lambda is at least e to the -12 root lambda -12. Now, what we're actually going to do is I'll put just down here a corollary of the geometric lemma. And it's actually this corollary which will be sufficient to prove the key lemma. I'll call it the geometric primed lemma. So it's just a corollary of the geometric lemma. And it involves basically grouping the possible answer in a slightly different way. So if you have case 1, you're very happy because you have probability at least 100th of a positive inner product in all of them, or at least -1. In 2, what? I mean, if you think about 2, suppose 2 happens, but lambda is like 0. I was always saying with 2, or you find a really impressive cat. It's not really a very impressive cat if you just know the other inner product's at least 0. It's not very impressive. Can't do much with that. And we've seen this number 2 to the 42 around. So instead, we're going to split either this happens or this happens for a small lambda, or this happens for a large one. Now, if this happens with lambda a bit smaller than 2 to the 42, then we're actually going to do something very wasteful. We're just going to say, this still wasn't a big enough boost, we're just going to use the t. So from the geometric lemma, you have either the E occurs and with probability at least, and I'll put just this, but with lambda is 2 to the 42. And you can check, this is just a calculation. We want something a bit bigger than this 2 to the e to the minus 2 to the 25. So you could do e to the 2 minus 2 to the 25, or 2, you have the second consequence, but with a large lambda, or there exists lambda at least 2 to the 42. And now we don't even need the e bar, we just use the large inner product. I guess there exists j, the inner product of sigma j u and sigma j u primed is at least lambda. This is probably at least e to the minus 12 root lambda minus 3. So that's just a consequence of the geometric lambda putting together in one, the case that either 1 occurs here or 2 occurs for a small lambda, at most 2 to the 42. You can see the bound here would be roughly the square of 2 to the 42 is 2 to the 41 times 12, something like 2 to the 24, it's a bit less than 2 to the 25. Doesn't really matter. But yeah, that's the consequence of the geometry. Good, so now our task is to show that this implies the key lemma. And the problem is they're still in different worlds, right? One of them is a geometric problem with some functions mapping into RD. The other is about colouring of a graph. So of course, we want somehow is the 3 different functions here should somehow be encoding neighbourhoods into the 3 different sets, y1, y2, y3. And the natural way to do that is to use a function which is basically an indicator function of the neighbourhood, but we'll just rebalance it because that makes the inner product behave more nice. So we'll just recall what PIs are, because that sort of matters. So PI, you can even define it between 2 sets, right? Between x and yi is the minimum over guys in x of the number of neighbours in colour I, yi, but this taken as a proportion, right? So that's the definition of PI between 2 sets. And the first thing we'll do is seems a fairly inefficient thing to do, but given that in the answer we just want this yi prime to have size pi times yi, then we can actually just all of the different neighbourhoods into yi. I can just restrict them all to have size exactly this, because they're all at least that. I can just throw away some neighbours and make it exactly. It just makes some of the calculations. So for all x in x, let n primes ix contained in n ix be such that it has size exactly pi yi. They're a bit inefficient. We threw away a little bit, but that's okay. And now we'll define the functions from, well, actually define this as a finite set. The finite set will be x. Call it S, x. And so define for each I, sigma I from x into, I should be doing into RD, but we'll actually go into R to the yi. Okay, these are all contained in RD if D is the max of the size of the wire. We just pick a space which is big enough to fill. By, and as I said, it's basically the indicator function of whether that point of y is a neighbour in the right colour. But we'll do a balanced one. So instead of doing 1 and 0, as you do an indicator function, you do 1 minus p or minus p. When I say that, but we'll also do a renormalization. So in the case where, I guess I'm talking about what is coordinate, little y. So if y is a neighbor, actually the n prime die of x, then we'll do 1 minus pi. Normalization is to divide by square root alpha I pi size of y. And the other one you do minus pi over the same thing, square root alpha I. This will be clear when we use it. Okay, so that's the situation. We've come up with a clever function to somehow express neighborhoods in terms of vectors. And now we want a clever lemma. I'm a little bit concerned by the way I've written things because I want space to write the lemma and space to prove the lemma. Now what I think I'll do is I'll put the lemma up the top and then we'll prove it down here. We have limited wall space, so we don't really have a lot of choices. I think that, you know, we'll leave the definition there. That's fine. And the lemma basically says that these inner products, or inner products of these vectors, are exactly what you need to understand the intersection between the neighbors. So if I do this for two different vertices in X, the inner product of these vectors exactly tells you how their neighborhoods in color I overlap. Okay. So that I be a color 1, 2, or 3, and that U and V be elements of X, then the following are equivalent. Okay. 1, the inner product is at least lambda when you factor these two different points into RD. Second, that the neighborhood, or n primed I U intersect n primed I V, is at least pi plus lambda alpha I pi lambda I. So this is like, well, if lambda is positive, it's a bit more than you'd expect. You have two sets of size pi lambda I. If they had completely, the expected intersection would be pi squared, right? So you're getting a bit more, lambda positive at least. And third, let's just look at the neighborhood intersection of co-degree here. But with respect to neighbors of U, then I'm saying pi plus lambda alpha I times this n I prime of U. So let's prove the lemma. We need to show they're all equivalent. Actually, it's obvious that 2 and 3 are equivalent by definition. Because the size of this is defined to be pi times size 1. Okay, so 2 and 3 are really the same thing. We put them all there because, you know, we really want the link between 1 and 3, and we're going to prove it by showing it's 2 steps. So now we need to show 1 and 2 are equivalent. And it's just a calculation. We'll do the calculation, but it is just a calculation. So let's see if what actually, I mean, we're doing it always greater than equal to, because again, when we apply it, that's sort of what's useful. I mean, it's true like this because it's true with equals as well. So it's sufficient to prove that your intersection of your two neighborhoods is actually exactly determined by this product, in the sense that if you do this, what would be minus. Maybe I'll drop I won't write all the i's, because the I, you know, it's writing I on every single thing. And it's, you know, so I'll just drop the I maybe. So we want to say this intersection minus p squared mod y should be equal, in fact, to alpha gamma p times the inner product. So it's kind of saying if this guy is equal to gamma, then this intersection is equal to this thing with that, sorry, lambda. If it's equal to lambda, this thing is equal to the equivalent thing with that lambda. And then obviously this product. Yeah. So the intersection of the neighbourhoods is exactly determined by a simple linear calculation, whatever, in terms of the inner product. And in a way, this is, yeah, let's say just a calculation, because you expand the right-hand side of this here, then you're doing the inner product of two vectors that look like this. Maybe before I do that, let's say, let's have notation A2 for the intersection of these two sets. I guess it's saying those elements which are in both, and therefore two of them. A1 for the symmetric difference. In other words, those elements that are in exactly one of these sets. And A0 for those that are in neither. Well, that's the number that are in yi minus the numbers counted in the others. And what can we say about the right-hand side? Well, if you do this in a product, well, one thing you can see is in every term, this is going to have a 1 minus p or a minus p. It'll also have this guy in the denominator. But if you multiply the denominators, it exactly cancels this term here. So this will exactly cancel with the term that's coming from the denominator. So we don't need to write any of that. And what we get is if you pick a value, or a vector, you know, because this would be like summing over the y's, what do you get? If you pick a y which is in the intersection, you get 1 minus p squared. This is for everyone in A2. You're going to get minus p, 1 minus p for everyone in A1. And you get plus p squared for everyone in A0. And then all you need to do is you need to notice that A0 and A1 are actually determined in terms of A2. Because A1 is, well, if you have one of the two, well, if you're in this one and not the other one, well, how many elements do that? Well, it's the cardinality of this minus the intersection. But the cardinality is exactly p times y, because we fixed cardinality. So this is 2 times p mod y minus A2. And you can do the calculation, that means A0 is 1 minus 2p times the size of y plus A2. And if you substitute, maybe we can basically switch it. I mean, all you're doing is, this was kind of made so it would work. You substitute these values in, you cancel, and it gives you A2 minus p squared mod y, which is exactly the left-hand side that we want to prove, right? So as I say, I mean, we wanted to do it because we wanted to go through the details of proof and check. But really, balancing the indicator function this way, it works its magic, and you get the intersections are exactly this nice expression in terms of the product. So this is, we can already see why this is useful, right? Because the geometrical element is going to give us some information in terms of the inner products. We want to translate that into information of intersections of neighborhoods, because this will feed into the conditions on the minimum degree. Good, so let's clear this. I'll leave the lemma, although perhaps I could even, perhaps I can get rid of 2, just have 1 and 3, right? Because that's what we're going to need. So this one is think maybe here in this consequence of the geometric lemma, let me just give them, call them G1 and G2. Just so they're different names from these 1 and 2 here, right? So we know which one. Talk about. Okay, so proof of the key lemma. What's the situation? Given this free coloring of the union of these sets, and we're given some values of alpha. And we want to choose a vertex, want to choose the color, choose the subset and all this, such that one of these two things occurs. Now, the one we're going to find is unsurprisingly, perhaps, just a direct consequence of what comes out of the geometric lemma. If it's G1, then we'll prove 1. If it's G2, we'll prove 2. So, basically the first thing you do is apply the geometric. So what do we do? Apply, I'll call it the geometric primed lemma, whatever this consequence of the geometric lemma, with, I guess, the finite set being x. U and U primes are just uniform, independent, uniform random variables in x, okay, because it's going to correspond to selecting just 2 points of x uniformly random. And with the functions, of course, sigma 1, sigma 2, sigma 3 can be just defined. Okay. If the result is G1, then what do we have? So we have probability of E is at least E to the 2 minus 2 to 25. What does that tell you? Well, of course, E was the event that all of the 3 inner products are at least minus 1. And these were inner products like sigma I of U, sigma I of U primes. And U and U prime are just uniform values of x. So if this occurs, it's saying at least this proportion of ordered pairs in x have the property that all 3 inner products are good. Then at least e to the 2 minus 2 to 25 mod x squared pairs, it's actually ordered pairs that could even equal. Use x in B, for some reason x B. In x have this, all 3 inner products at least minus 1. Okay. Now, we want to find one vertex, which is in quite a lot of these. Okay. We want more than that. What we want to do is we want to pick a vertex, and this vertex is good for some number, right? Well, we can do that. Let's do one more step thing. So now there exists x in x with at least the same thing, but now I'm going to put just x instead of x squared. So x is still the first coordinate, but v is just vector at x, right? You know, because this is the total, you can find one of them that achieves at least that divided by x, right? Just by pigeonhole something. Now, we'd like actually to choose a bunch of neighbors of x that are all joined to x the same color. And then we can do this color set. We can do this, we can find this thing which is red. So what do you have? Just observe, if you have a number d minus 1 over 3 is at least d over 4. If d is at least 4. So basically, this number so far as counting neighbours that are good for all three inner products, but you don't know what the colour of those edges are. But at least a third of them have to be in the same colour. Okay, I put t minus 1 over 3 because you may have x to your 7 here as well. But you know, you can now say there exists one of the three colours, and at least e to the minus 2 to 25 x pairs xv, which still have the same property, but such that those pairs are all coloured the same colour. And all xv are, well, I could put all of these v, these v are in the neighbourhood colour I. So we could let x primed be this set. X primed is big enough for the condition we wanted. And it won't be difficult to check that the minimum degree condition works out, because for all v in x primed, what can we say? I should say x primed will be this set, y primed will be the neighbours of x on the other side, ni primed of x intersect yi. And now for all v in x primed, what can I say about the neighbours of v in yi primed? It's at least, well, it's exactly this thing, right? With what, u equals x. And because the inner product is minus 1, you have this conclusion with lambda is minus 1. So you have pi minus lambda I. Pi minus alpha I times size of y prime. And this is exactly saying that you have a minimum degree condition between the sets afterwards, which is like the minimum degree condition before, minus alpha. So with that, you get conclusion 1 of the Q lambda. The idea was we get some number of pairs that are good for all three colour steps, at least from the point of view of minimum degrees, really, the inner product thing. And then at least a third of them are coloured in the same colour, and we use those. And that's all we did. Okay, so now we need to do the second case, because it could happen that the result is G2. We don't have control of what the geometric lemma throws at us. Actually, this case is easier because I have less to verify, really. I don't have to check things are in neighbourhoods, because all I'm going to do is go down to a subset where I get an increased degree. Right, so if 2 occurs, then the sum I, and yeah, just sum I, then we have a good probability that the inner product is large, at least lambda. So there is lambda in this 42 as well. This is e to the minus 12 root lambda minus 12. Now what can we say? Then this means, so there exists at least e to the minus 12 root lambda minus 12 x squared pairs, uv, let me say xv in x, such that this occurs, such that the inner product is lambda. So there exists x such that there are at least, again, justified by the size of x, so at least e to the minus 12 root lambda minus 12 sides of x, vertices v in x such that. And now that these can be our x primes, you notice in the second case, we don't even need the x prime to be contained in a neighborhood or anything. We're not doing a color set. We're not going to put little x in the book from the point of view of the algorithm. I know I'm kind of all the time talking about the lemma, talking about the algorithm as well. The lemma's there to do the thing we can do in the algorithm. In this case, we don't even do a color set, so we don't need any restriction on x primes. It happens that y prime will still be its neighborhood on the other side, but it's just the case. It doesn't even matter that. Okay, so what do? We set x prime to be the set. In other words, the set of v that do that. And we have x primed is at least e to the minus 12 root lambda minus 12 times the side of x. And y primed is the neighbours in primed x sec yi. And again, by the lemma, for every v in x primed, it's the same argument, but now we're going to have a nice positive lambda instead of minus 1. You're going to get with the name ni primed v sec yi prime is at least pi plus lambda of y times y primed. Dividing by y primed gives you exactly the result we wanted in terms of the increase of the degree. So, okay, these are important details, but it gives the okay, so let's remind ourselves basically quickly how the algorithm works. So we call it the book's algorithm. You start with these sets x, y1, y2, y3. You're going to build books in three different colors. And you're going to use t's to denote the bit which is the clique. So at the start, t1, t2, t3 are empty. And I mean, it's not necessary to define the algorithm, but in fact, in the theorem we're trying to prove, the book theorem, you start with the minimum degree conditions all being close to a third. So I may as well put this like as a fact here, that you're going to have P1, P2, P3, each at least a third minus delta. Actually, for the stuff we do today, the value of delta is not so important. I think it's useful to suppose it's at least, close to 6 or something. It's not too important. But the application delta will actually be 2 to the minus 40. Okay, and what do you do at each step? At each step, well, first you do the definition of alpha in each color, which is how much you're willing to lose in each color. So you define alpha I to be, you look at your current density or your minimum degree condition in color I minus a third minus 2 delta, and you divide by t. Again, maybe t is another thing where, technically speaking, what we do today is not super dependent on the value of t, but it's actually going to be k over 2 to the 30 when we capture. I think all we're going to use today is t is sufficiently large. Okay, and then what you do after this, you do either 2, you do a color step, which involves, well, it's basically you apply the key lamp, which kind of mostly rubbed out, but you can see the conclusion of it. If you get case 1 of the conclusion, then it's saying you're in a good situation to do a color step in color I. So you add the vector, the vertex x to, well, I guess you could say you update set ti to be ti union x. You restrict x to be x primed. X primed is the set that comes up here. You restrict yi to be yi primed, which is of course contained in the neighborhood of x in the right color. And let's just note over here, there's lots of properties that might matter, but I think for us today, the most important ones will be about the evolution of the minimum degree condition. So in this case, you might lose alpha. So actually, we'll introduce in a minute, like S as counting which step you're in. So if S is a color step in step I, then here you might go down by alpha I. And in a boost step, the other type of step, your density will of course go up. But here you just x is restricted to x primed and y to y primed. I'm going to put it over here then. And the density goes up. Pi s after the step is at least the previous one plus lambda. Okay. So yeah, the rest of the class today, we basically want to see a lot of properties of the well, the evolution of the minimum degree and how that relates to the boost, the number of boost steps, the properties of boost steps. Because as I said, the boost steps are in a sense the thing that makes the argument feel possibly wasteful. So you need to check, we've set things up in a way that actually they're not too wasteful. So let's see what we can say about that. I guess we just carry on there. So min degree, well, there's the PIs, and boosts. What can we say about them? This is given, yeah, by the letter as well, because the letter says in one of the colors. Yeah, choose it, please. In both cases, you're doing this in one of the 3 colors. And in fact, that's important because this is about one of the things we'll say right here is so we can we'll use a S to denote the number of steps, right? Because first we're saying X, Y, I. Of course, these are updated every step, so they're different sets every step. So they're XS, YIS, TIS, alpha IS. Well, actually, I'll do alpha afterwards. So V sets after S steps. And we'll let alpha IS be PIS first, right? PIS will be the density minimum degree condition between the XS and YIS. In other words, the minimum over guys in here of the density color I to that set. And obviously the alpha IS is a function of this. So in a way, the alpha you use is actually the alpha for time s minus 1. You look at what you have currently, and that's what you use to decide your next choice. And basically, the algorithm, I didn't really put it in here, but it has a rule for when it stops. It's useful that x always has at least some reasonable size, like e to the 2 to 25. And it's also, our objective is to get one of these sets t, which is the Kleek number, up to size equal t. So we stop when one of those happens. Let's use tau for stopping time. It's the minimum s such that either x of s is small, less than e to the 2 to 25, or one of the ti's gets up to size t. So we're actually going to prove that it's always the second case, right? Because we always will be successful finding the book. But a priori, you don't know which is going to happen. This will be ti of s. And now, given that you're going to have tau as the total number of steps, you can divide the steps into those that were boost steps in one of the 3 colors, and those are the color steps in one of the 3 colors. So this is actually a partition of all the steps. So if step 100 was a color step in color 3, then I'm saying 100 belongs to C3. Right? I don't want to write all that down. You can partition all the steps depending on whether they're boost steps or color steps and in which color. Now the evolution of the minimum degree will be a function of these, of which type of step you do in each step, right? So let me put it as a lemma. I know we messed up we used to call this lemma in the other one. Let's call this lemma 1 here, lemma 1. And it's going to be a statement about how the PI evolve. So PI of S is at least. So the first one will be a boost step. If you do a boost step, it will increase. So if the previous PI of S minus 1 plus lambda alpha, the alpha is actually alpha I of S minus 1 as well, right? Because you look at what you had and use that to decide your alpha. And this is if S is a boost step in color I. If you do a color step in color I, then you're willing to lose alpha, so that alpha of S minus 1. If S is a color step in color I. And finally, unchanged, or well, at least than it was before, otherwise. So this lemma is actually quite easy. I don't actually know whether it's worth writing anything down, because it's what we already remarked here, right? If you do a color step in color I, then you're willing to, you might decrease a bit in that degree condition. Like this one, if you get a boost, you boost by, I should put here lambda, I should put lambda of S. So when you do a boost step, there's some lambda at least 2 to the 42, and you can, note it down, right? Because they could be different for every different step. So lambda of S will denote the lambda that you get in step S. And the final one, why is this true? Well, if you're doing something else, then you're doing a color step or boost step in a different color. Let's think about that. So let's say you're doing a boost in color 2. So you're going into a subset of Y2, you're in a subset of X. Because we're working with a minimum degree condition instead of a density condition, the minimum degree from here to Y1 is at least the minimum degree you had from the whole of X to Y1. Just because the minimum of a subset is at least the minimum over a whole set. So that's why you have this final point. You can actually express this in a slightly different way if you write it in terms of, and I think this is a nice way to think of it, you can see our alpha is very much concentrated on how much are we above this value. This value being a third minus 2 delta. So you can think of this as kind of a surplus, okay, above the minimum. Right? So P star I of S will be Pi of S minus what we consider to be small value of third minus 2 delta. Now, the same statement implies what for this? Well, I mean, here you just have the P star of S minus 1, right? Plus, you know, I mean, there's some sort of, they're linear, right? If I add something to this, I also add it to that. Right? If I add, you know, 0.1 here, I add 0.1 to that too. So if this one increases by this amount, well, so does the P star. But what's it increasing by? Lambda S, times the corresponding alpha. But the corresponding alpha is just Pi star over T. So in this case, I kind of have my own value plus lambda alpha, and alpha is my value over T. So in this case, I'm at least 1 plus lambda S over T times my previous value. I have 1 minus 1 over T in the second case. And of course, I just have my previous value if I do anything else. Yeah. Okay. Now we make an observation. At the start, your surplus was at least delta, because we said consider the original degrees of this third minus delta, and this is comparing to third minus 2 delta. So now, what you can think of is what you get to time S is really at least your initial value times the product, because these are now multiplicative statements, right? You release you release this multiple of your previous value. In that case, this multiple in the second case. So what do we get? We get a 1 minus 1 over T for every color step. Color steps up to time S. And we get products over J, a boost step up to time S. And you get 1 plus lambda J over T.
This delta is fixed throughout the.
Yeah. As I said, in the final proof, it's going to be 2 to the minus 40 or something. But this whole section, or whatever we're doing now, it could be any value. I think it's useful that it's the most thick for this to be a sense of things. Right. And now I'm going to get rid of level 1, because actually we're going to do something better than that. Well, it's just a consequence, but let's call it fact 1. And it's basically this, except these steps aren't that interesting. In particular, how many color steps you're going to do are most T. So this is at least 1 minus 1 over T to the T, which is always at least a quarter. So from this, you in fact have your kind of surplus thing is always at least delta over 4 times the product over boosts, J, of boost and color I. We can even do the product over all of them, right? 1 plus lambda J. Oh no, so it's a tie next, anyway. I think we're only going to need to consider this at the end. I mean, that's when you get the best inequality, because these are all. So maybe the final surplus, BI. And this is going to be obviously an upper bound for this guy, because we're going to use this as a most one. The increase in density is always a most one. So this is going to be a useful fact. Another consequence of what we saw here, well, one consequence of this is this product is always at least one. And so your surplus is at least delta over 4 all the time. So I'll put it, it's kind of two things, but I'll put them both as fact 2. Your surplus is always at least a quarter of delta over 4. And so your original density, your original PI, is always at least, would be a third minus 7 delta over 4. You could put minus 2 delta for all really count. And there's also a useful fact about the alpha. If this is always at least delta over 4, then your alpha I of S is always at least delta over 4t. Okay, these statements are all live from that. Okay. You can obviously see how this particular statement has been pretty useful when we're trying to calculate in the next class, like through the evolutionary algorithm, how much do the sets go down in size? Well, if your minimum degree to the other side is always very close to a third, that means you have good control over the size of the neighborhoods you're going into as you go through the process. Okay, so we got that. What else? Okay, so we want to have another bound, which would just be the total number of boost steps. We want to say you can't have too many. Okay. And that's sort of clear because when you have a boost step, you multiply by this factor, and this guy up here is at least 2 to the 42. So if t is sufficiently large, which it will be when k is sufficiently large for that, then let's just say 1 plus 2 to the 42 over t is at least e to the 2 to the 41 over t. I'm just basically using that inequality 1 plus x at least e to the x over 2, which works for small x. And if t is large, then this counts. So as you have that, we have at every boost, at every sort of lambda j is at least 2 to the 42. So you always win a factor that's at least this big in every term. We have that, whatever, e to the 2 to the 41, oh, it's over t. But you win one of these terms for every boost, so times the set of boosts. This has to be at most like 4 over deltas, because this is always the most one. Right, so then you just take logs on both sides, and then you get applies, just take logs on both sides. BI is the most, okay, t over 2 to the 41, log 4 over delta. I think this guy, because delta is much smaller than a quarter or something, let's just say this is the most t over 2 to the 40 log whatever delta. So I'll put that as fact 3. Total number of boosts is at most t over 2 to the 40 log whatever delta. I mean, yeah, these bounds, they don't seem so inspiring when you just go through and write them, but they're already coming out of this situation we set up. If you have a pretty big boost, you can multiply them all together, and it can't multiply up to any bigger than 1. And that tells you can't have very many. Okay. So the last challenge we really have today, the last thing we want to prove about boosts is something about the sum of the square roots of the lambdas. Now that might sound strange, but if you remember, when we're doing the boost step, how much does the x go down by? You have e to the minus 12 root lambda minus 12. So if you do this lots of times, you're going to have lots of factors of root lambda. And if these are very big, then maybe doing this lots of times would kill your set x. So it's important to have a bound on that as well. I think in the proof we're just going to use, but this proof right here, we're only going to use fact 1. So I may as well get rid of these for now. I think for this proof we're just using fact 1. Okay, so lemma 2, if I sum square root of lambda j over all the boosts, this is at most, I think you can say 2 to the minus 20 t log 1 over delta plus 4 delta to minus 1 root. So I mean, I just put up these numbers. Don't worry where these numbers come from. These numbers come from the proof. And so let's just do the proof really, I guess. So it's useful to actually split the boosts into kind of small boosts. Well, they're not that small, but anyway, quite small boosts and very big boosts. And when it's something very big, it's related to the, if you think about what you win here, right? What you're winning is 1 plus lambda over t. I mean, partly I'm just saying, in the proof, we're thinking about how do we approximate this with exponentials, because everything's easier to approximate with exponentials, whatever. Well, yeah, again, when this part is small, 1 plus x behaves a lot like e to the x. But when this is big, not at all. So we may as well split into small and large when this is like a constant. And it happens to make sense, weirdly, I'm going to do it with e minus 1. E minus 1 here is the time when this whole thing gets up to be. It just becomes a convenient place to. So let's take the small boost, and I'll do a little circle. VI open circle is the set of J in VI, the set of boosts in color I, but where the lambda of the boost is between 2 to the 42, which is always the lower bound, and let's say e minus 1 times t. just some kind of upper bound. Obviously, there's been pretty big boosts to that. And let's have the solid circle I is the rest. So the boosts are even bigger. Okay. So what can we say about this sum just over the small boosts? Well, first, let's bound the total sum of the lambda j's over the guys that are small boosts. How do you think we could control this? Well, let me put 2t there. We'll just see. Let's just say 2. Right. So okay. I think it was 2t. So e to the x over 2 is less than or equal to 1 plus x, right? When x is small. And I think it works out to x that. So lambda, in other words, you take logs on both sides, like it's x over 2 is less than or equal to log. Okay, so these guys, if I sum the logs of these guys, we know it's the most log of 4 over delta. Because, well, this is the most 1, so this product's the most 4 over delta, and then I just do logs on both sides. Log of this is the most log of 4 over delta, and then a log of a product is the sum of the logs. So the sum of the logs of these guys is most log of 4 over delta. And so this sum is a most log 4 over delta, because this is a lower bound for the sum here, because the x over 2 is most log 1 plus. And I'm just going to use this the most 2 log 1 over delta. It's just a detail, but you can basically get this bound on the sum of the lambdas as a consequence of the sum of this fact 1. And now, well, now you're happy, right? Because you're summing roots. You can get some bound just by considering the square root is at least the original value over the square root of the minimum it can be. Right? So this is at least, what I'm going to do is I'm going to square root, divide by the square root of the smallest value this can take. And the smallest value can take is 2 minus 42, square root is 2 minus 21. So I have this. So 2 minus 21. This guy, I mean, this is 2 minus 19. Actually, I always get mixed up with what they. Anyway, it's not about. Anyway, so this sum is most that, and the sum of the lambda j's is at most 4t log 1 over delta. So this is most 2 minus 19 t.
And you see what that is.
No press. Right, so it's most this, because each one gets to be the lambda j, and it's divided by the smallest possible square root. And that gives you this term. So all that remains is to show that the big boosts can contribute most that. So that won't be too difficult. And then we'll have established all of the information we need to go into the final proof about the mean degree and the boosts. So I think that the big boost are actually going to be easier because we'll just use two facts. We'll use that there's a limit to how big even a big boost can be, and there's an easy bound on the number of them. So it'll be, in fact, slightly simpler even, but it follows from using fact one, again, fact twice. So what do we get out of fact one? So by fact one, what can you tell me about the biggest boost possible? Well, if this was so big that this was bigger than 4 over delta, then you just immediately have a problem. So by fact one, the maximum of the lambda j to most. Well, if one of these is big as whatever 4t over delta, you'd immediately have boosted your degree by more than 1, which is impossible. So 4 delta minus 1 t. And what can you say about the number of big boosts? Well, every big boost is bigger than a multiple of E here, right? Because if you're not in the small boost, then your lambda j is at least E minus 1 t. So this guy's at least E. And so your density is in particular at most, what you've totally boosted is at least delta over 4 E to the number of big boosts. Well, then immediately the number of big boosts is the most log of 4 over delta. Right, so in particular now summing square root lambda j over j big boost. What we're going to do is the number of them is the most log of 4 over delta, and each one is the most the square root of the maximum. So what we get like 2 delta minus a half t to the half. Yeah, and I think maybe there's some just using some inequality in log 1 over delta is most delta minus a half. There's some inequality here. Yeah, and then that's the most 4 delta minus 1. So yeah, we've used a different argument for each of the two types, and first type is mostly the same. Now, actually, with all types of arguments like this, in some sense, the real thing you care about, doing the proof and everything being correct, one of the two types kind of dominates or is more important. And really, it's the smaller boosts here are kind of more important for the sum, because the big boosts here are root t. I mean, maybe the dependence on delta is worse, but delta's a constant, t goes to infinity. So really, the very big boosts, if your opponent tries to give these very big boosts, it's not a good approach for the end. It's not costing you very much in this way, and it's obviously helping you with this. So I think that's roughly what we wanted to say about mean degrees and boosts. In a sense, it's auxiliary stuff, right, to understand how the algorithm behaves in practice. But now we're in a pretty good shape to finish off the rest of the proof next time. I don't know, it was a strange decision, but I kind of thought it'd be interesting once to like prove something in class like this. And really, it's just about short enough you can actually do it all, right? So I felt that temptation. I know it's going through quite a lot of details. But so hopefully we'll do it next time. We will complete the details and see it really does work. We'll also have at the end a little bit of a discussion of what were the parameters involved here and why was it kind of clear it should fit together and work. Because that's kind of often more interesting than just, oh, it did work. I mean, yeah, because I mean, some of these choices are a bit arbitrary, it's 240s, but it's fine. Okay, so I think that's good for today. Cheers, and yeah, see you for the last class on Thursday. Ta-ta.